It includes Matplotlib, which is a plotting library used for creating visualizations such as charts, graphs, and histograms. The multiprocessing module supports concurrent execution using processes instead of threads, while Seaborn, built on top of Matplotlib, is utilized for creating more attractive and informative statistical graphics. Pandas is a library for data manipulation and analysis, especially with labeled data structures like data frames. Nuby, the fundamental package for scientific computing, provides support for large, multi-dimensional arrays and matrices. Pygmo, a Python library, aids in general-purpose global optimization using evolutionary algorithms. The OS module offers a portable way to use operating system-dependent functionalities. And the time module includes functions related to time. Additionally, Numba acts as a just-in-time JIT compiler for Python functions to enhance performance. The SEPI stat submodule from SciPy is used for statistical functions and probability distributions. For working with date and time, the DataTime module is employed. FunTools provides higher-order functions and operations on callable objects, whereas ITERTools offers efficient looping constructs. By importing these libraries, the code gains access to a wide range of functionalities necessary for data processing, visualization, optimization, parallel processing, statistical analysis, and computational efficiency. Each library serves a specific purpose, collectively offering a versatile toolkit for various data science and scientific computing tasks. This code snippet imports various functions and modules from different files, including Diversify, Portfolio Utils, Returns, Stats, and Utils, each providing specific functionalities related to financial operations and calculations. The Diversify module primarily contains functions related to diversification. Portfolio Utils offers functions for managing portfolios, such as normalizing weights, calculating weighted returns, fixing correlation matrices, and checking correlation matrices. The Returns module focuses on calculating financial indicators like maximum drawdown and maximum pull-up. The Stats module is used to compute statistics such as the normal probability of loss and normal probability less than specific values. Lastly, the Utils module consists of general utility functions like linear mapping. These imports are crucial for modularizing finance-related operations, effectively organizing the codebase, reducing redundancy, and facilitating a structured approach to developing financial operations. This code snippet imports essential functions and variables from the SymFin library, facilitating access to financial data such as stock prices, fundamental data, and other financial metrics. The imported variables, including total return, close, volume, ticker, sales, and date, represent the names of columns in a financial dataset, enabling easy reference to specific columns. Additionally, the variable days per year likely stores the number of business days in a year, a common parameter in financial calculations. Utilizing these imported functions, variables, and dataset names simplifies financial analyses, calculations, and data manipulations, contributing to more efficient and cleaner code. Furthermore, employing meaningful variable names enhances code readability and mitigates potential errors that could arise from manual entry of column names or other data-related details. The provided code snippet initializes a random number generator using the NumPy library with a specific seed value. Using a seed value makes the generation of random numbers reproducible, ensuring that if you run the same code with the same seed multiple times, you will get the same sequence of random numbers. This reproducibility is particularly useful for debugging or testing code that involves randomness, as it allows the recreation of the same random conditions. In this instance, the seed value chosen is 81,680,085. A comment within the code humorously attributes the cause of the Big Bang and all universal matter to this specific number. While not scientifically accurate, this playful remark underscores the significance of the seed in random number generation. This code snippet ensures that a directory for storing plots related to portfolio optimization exists. It checks if the specified directory path plus portfolio optimization is already present using the JOS path exists function. If the directory does not exist, it creates it using JOS makers. This step is crucial because it is necessary to confirm that the directory where files will be saved is available. By creating the directory if it doesn't exist, this code prepares the required structure for storing the plots generated during the portfolio optimization process and ensures that no errors occur due to missing directories when attempting to save the plots. This code snippet is from a financial data library called SymFin, which provides access to company financial data. The first line, SHISF, Set data dir SimFin data sets the directory where SimFin data will be stored or accessed. In this instance, directing it to SimFin data, the second line is code abiki pat SimFin abiki test default key for you loads the API key required to access SimFin data. The specified file SimFin API test contains this key, defaulting to a free access key if no key is available. Using this code is crucial for accessing SimFin data. Setting the data directory ensures that the downloaded data is organized, while loading the API key is essential for authentication and access to the financial data provided by SimFin. This code snippet involves configuring settings in Matplotlib for plotting purposes. It disables the offset notation on the e-axis of plots by setting axis formatter qscof set to false, ensuring that large numbers won't display in scientific notation with an offset e.g.6. It also creates a couple of formatter functions to format numbers on plot axis. Ept formatter 0 formats numbers as percentages with 0 decimal places, whereas shift formatter on adds 1 decimal place to the percentages. Additionally, it generates formatter functions for scientific notation. Set formatter 0 formats numbers in scientific notation with 0 decimal places, and set formatter on applies 1 decimal place. These settings and formatters can be employed in Matplotlib to control the appearance of numbers on the axis, thereby enhancing the clarity and readability of plots for visualization and analysis. This code configures the plotting style for Seaborn, a Python data visualization library, by setting it to WideGrid. By doing so, it ensures that plots have a white background accompanied by grid lines. Selecting a specific style for plots can greatly enhance their aesthetics and readability, making the visualizations more appealing and easier to interpret. Different styles can be chosen based on personal preference or the specific requirements of a project. The WideGrid style, in particular, offers a clean and structured background, aiding in the clear distinction of data points and other visual elements. The code defines 3 variables, smalls, and big, representing different sizes for plotting figures. Each size is defined using a tuple with 2 elements, where the first element indicates the width of the figure and the second element denotes the height. These predefined sizes can be employed when creating plots or figures in a graphical library, ensuring consistent appearance across different parts of the program or project. Consistent figure sizes contribute to more appealing visualizations, making them easier to understand and more professional looking. This uniformity aids in maintaining a cohesive layout in visualizations, facilitating easier comparison and interpretation of the presented data. In summary, using these predefined figure sizes helps maintain consistency, improve visual appeal, and enhance the readability of plots in data visualizations. The code defines a function designed to calculate 1 period returns from the provided share prices. The input is a pandas data frame named prices, which houses the historical prices, and a Boolean future that decides if the calculation targets future returns true or past returns false. The function begins by calculating the percentage change in prices using the data frame's change method, subsequently adding 1 to these values. This results in 1 period returns, where, for instance, a value of 1.5 indicates a 5 gain and 0.98 indicates a 2 loss. If the future parameter is set to true, it proceeds to shift the returns 1 step backward using the shift method, which helps in projecting future returns based on current prices. The final output of this function is a pandas data frame containing the computed on-period returns. This functionality is particularly valuable in finance and investment analysis, facilitating quick assessments of investment returns from historical data. Additionally, the capability to calculate future returns aids in making informed investment decisions and evaluating the potential performance of various assets. This code snippet demonstrates how to use the SimFin library to load daily share price data for US stocks. Initially, the time command, a special Jupyter Notebook command, is utilized to display the time taken to execute a particular cell. Subsequently, a stock hub object is created from the SimFin library, configured for the US market with a setting to refresh share prices every 100 days. Following this, the stock hub object uses the load share price method, specifying the variant daily parameter to load the daily share price data for US stocks. This approach is practical for fetching and using financial data for analysis or research purposes. By employing SimFin, users gain access to a comprehensive range of financial data, including balance sheets, income statements, and share price data, which can be utilized for various financial analyses. modeling, and decision-making processes. Moreover, the TimeMagick command records the time taken to load this data, enabling users to monitor the performance of data loading operations efficiently. This code segment employs the ValSignals function from the Hub module to calculate valuation signals like sales using financial data automatically downloaded by the function. The TimeMagick command is included to measure and display the execution time of this operation. The ValSignals function likely retrieves financial statement data, such as revenue and market capitalization, to calculate valuation metrics like the price-to-sales ratio. This process is automated and efficient, eliminating the need for manually gathering or processing the data. The result is a data frame of ValSignals that contains the calculated valuation signals for further analysis and decision-making. By using this code, time and effort are saved through the automation of fetching financial data and deriving valuation signals, thereby enabling quicker and more informed analysis and decision-making based on these metrics. This code processes a pandas data frame representing daily stock prices in total return format. Initially, it extracts the total return series from the data frame, reshaping the data into a matrix where each row corresponds to a time step and each column represents an individual stock ticker. Subsequently, it removes rows time steps that contain insufficient data by dropping rows with non-values in more than 10 of the columns. Additionally, it eliminates the last row, as this row may be incomplete due to the timing of data retrieval or recording. The end result is a cleaned and processed data frame of daily total return stock prices, ready for further analysis or visualization. This code is vital as it ensures the data is in the appropriate format for downstream analysis and excludes any incomplete or unreliable data points that might negatively impact the analysis. This code snippet calculates the daily stock returns from the total return data provided using a function named JONA-period returns. This function computes the daily returns based on the given daily prices, with the parameters future truth indicating the calculation of returns from today to tomorrow. After the returns are calculated, the code removes any empty rows, primarily focusing on the first row to clean up any invalid or incomplete data resulting from the calculations. The code then displays the first few rows of the data frame that contain the calculated daily returns for each ticker, with columns representing individual stocks and rows representing time steps. This process is useful because it converts the total return data into daily returns, facilitating easier analysis and comparison of different stocks' performance on a daily basis. By providing daily return data, investors can gain a better understanding of the volatility and performance of individual stocks or their portfolio. This code snippet extracts all the stock tickers from a data frame named daily price and stores them in a list named HAL tickers. Stock tickers are unique symbols assigned to publicly traded companies for identification. The columns attribute in pandas refers to the column labels in a data frame, and the toList method converts these column labels into a Python list. This extraction is useful for obtaining a comprehensive list of all stock tickers present in a dataset or data frame. With all the tickers in a list, it becomes easier to iterate over them for further analysis, data manipulation or visualization purposes. This code snippet filters out ticker symbols based on their median daily trading market capitalization being less than $1 million. First, it calculates the daily trading market capitalization for each ticker by multiplying the closing price and the trading volume from the provided data frame at daily price. Next, it determines the median of these daily trading market capitalizations by grouping the values by ticker symbol and finding the median for each group. Following this, the code creates a mask to identify tickers whose median daily trading market capitalization is less than $1 million. Then, using this mask, it filters out the ticker symbols that meet the condition and stores them in the SPED ticker SONA variable. To avoid duplicates, it finally extracts unique ticker symbols from these filtered results. This code is particularly useful in financial analysis or stock market studies to identify stocks with relatively smaller daily trading market capitalizations, providing a basis for further analysis or investment decisions. By identifying these bad tickers, one can refine investment choices or enhance risk assessment strategies. This code snippet filters out tickers whose maximum daily returns exceed 100. It achieves this by first creating a mask-2 that identifies tickers with daily returns greater than 2.0, equivalent to a 100 increase. It then checks if at least one ticker meets this condition by summing the true values in the mask. Finally, the code extracts the tickers that satisfy this criterion and stores them in a list called BUD tickers2. This process proves useful in financial analysis or when dealing with stock market data, as it helps identify extreme price movements by pinpointing tickers with maximum daily returns exceeding 100. Investors or analysts can investigate the reasons behind such movements and take appropriate actions, such as conducting detailed analyses, implementing risk management strategies, or making informed investment decisions. The provided code aims to identify and extract stock symbols tickers with a significant amount of missing data in a dataset. Specifically, it focuses on tickers with more than 20 missing values (NaN). The process begins by calculating the number of NaN values in each column of the daily return sol data frame using the expression daily return sol. ISNA, Sumaxis zeros. This computation results in a series where the index corresponds to column names tickers and the values represent the count of NaN values in each column. Next, the code checks if the count of NaN values exceeds 20 of the total number of rows in the data frame. This is achieved with the condition daily return sols, ISNA, Sumaxis 00, to len daily return sols. The outcome of this condition is a Boolean series mask indicating whether each ticker has more than 20 missing values. Finally, the tickers satisfying this condition are extracted. The index values tickers where the condition is true or converted to a list, which is then assigned to the variable SPED tickers trees. This code is crucial for data cleaning and analysis as it identifies tickers with insufficient data, thereby ensuring the quality and reliability of subsequent analyses. This code snippet filters through a list of stock tickers, shell tickers, to identify those that end with the suffix old, indicating that these stocks have been delisted. The code uses a list comprehension to check each ticker in the shell tickers list and adds it to the but tickers for list if the ticker name ends with gold. This approach is useful for identifying delisted stocks with this specific suffix, providing crucial information for further analysis or decision-making related to investment strategies or portfolio management. The code snippet creates a list named SPED tickers 5, which contains tickers known to have problematic or erroneous data. In this instance, the list includes only one ticker, thus, this list is intended for use in data processing pipelines or analysis scripts to filter out or handle the data linked with these specific tickers separately from others. By identifying and flagging such tickers in advance, it helps prevent errors or inaccuracies that could result from using data associated with them without appropriate handling. The code in question combines multiple arrays of bad tickers into a single array. Initially, it concatenates all the arrays together using the NINP concatenate function to create one unified array. Following this, it utilizes INP unique to extract only the unique elements from the concatenated array, thus ensuring that no duplicate bad tickers remain. The final step involves calculating and returning the total number of unique bad tickers. This code is particularly useful when working with multiple lists of bad data, in this case, bad tickers, and the necessity arises to consolidate them into a single list while eliminating any duplicates. By doing so, it simplifies the process of managing and analyzing multiple arrays by merging them into one unique list. The code snippet is designed to generate a list of valid stock tickers by performing a set difference operation between the list's all tickers and bad tickers, subsequently sorting the resulting unique tickers alphabetically. Initially, two lists of stock tickers are given, all tickers and beta tickers. To ensure uniqueness in both lists, the set data type is utilized. A set operation is then used to find the difference between the set of all tickers and the set of bad tickers, resulting in a set of valid tickers. This set of valid tickers is converted back to a list, which is then sorted alphabetically using the sorted function. The length of the valid tickers list is obtained and returned, indicating the number of valid stock tickers. This code is particularly useful for filtering out invalid stock tickers from a list of all tickers. It plays an essential role in data validation and processing in financial applications, where only valid tickers are acceptable for further analysis or processing. This code snippet generates copies of two original datasets, daily price and daily return sol. For a subset of tickers identified as valid tickers, these duplicates, named daily price and daily return storg, are essential for preserving the initial data before any modifications or imputations occur. Preserving the original data serves multiple purposes. It provides a historical reference, allowing for comparisons and maintaining a record of raw data for auditing. It also ensures data integrity by preventing modifications made during analysis or cleaning processes from affecting the original datasets. Additionally, the unaltered data may be necessary for plotting or visualization purposes. As suggested by the comments in the code, overall, creating copies of the original datasets is a standard practice in data analysis. It helps maintain data integrity, promotes reproducibility, and supports various stages of data processing and analysis without altering the primary source data. The given code addresses the issue of missing share prices by carrying the last known value forward or backward and recalculating daily returns based on these filled prices. This is crucial for maintaining consistent and complete data across a portfolio of random stocks, ensuring that all daily share prices are available for the same dates. By filling in the missing prices, the code ensures the analysis is not restricted to the dates where all stock prices are originally present. This allows for a more extensive and meaningful analysis as it covers a broader time range. The method assumes that any period with missing share prices represents cash in the portfolio, which does not fundamentally impact strategies like buy, hold, or threshold. However, it could affect strategies like a rebalanced portfolio if the intention is to use only the original share price data without any filling. This can be easily adjusted by changing the statement from if true to if false. Overall, the code ensures that daily share price data is consistent and complete across the portfolio, facilitating more robust analysis and modeling of different investment strategies. The provided code filters the daily returns data to include only the information for valid stock tickers, leveraging the list of valid tickers to selectively extract relevant data from the daily returns all dataset. This filtering process is crucial as it guarantees that any subsequent analysis or calculations are both accurate and pertinent. By eliminating the invalid tickers, the data is effectively cleansed, ensuring that only necessary and valid stock-related information is considered. This step helps in preventing errors and discrepancies, thereby enhancing the reliability of the analysis. This code likely displays the daily returns of stocks as a data frame, which is crucial for providing insights into their performance and volatility over time. Analyzing daily returns helps investors make informed decisions about buying, selling, or holding stocks in their portfolio. By visualizing and examining the daily returns of different stock tickers, investors can identify trends, assess risk, and optimize their investment strategies. This code snippet iterates over each element in the list of valid tickers, printing each stock ticker symbol followed by a comma. This approach allows all the ticker symbols in the list to be displayed on the same line, separated by commas. The primary purpose of using this code is to offer a concise and easy-to-read summary of the stock ticker symbols being used or processed in a specific section of the code. Such a summary can be beneficial for debugging purposes, logging, or displaying information to the user, enhancing overall clarity and readability. This code calculates the future mean annualized stock returns for a specified range of years. In this case, 2 to 3 years. First, it sets the minimum and maximum number of years, using variables min years and max years. It then defines a constant, future returns. To label the data for later plotting, the core calculation is performed by the change function from the Cymphin library, which takes a data frame containing daily stock prices daily priest, a frequency parameter b to denote business days, and specifies the calculation of future and annualized returns within the range of 2 to 3 years. The purpose of calculating these future mean annualized stock returns is to analyze potential long-term investment performance. By examining historical returns over the defined period, investors can make more informed decisions regarding future investments. The code defines string constants to represent various types of return data, portfolio types, trial numbers, and statistical measures, including the number of stocks, arithmetic mean, and geometric mean, among others. These constants significantly enhance the readability, maintainability, and reliability of the code by eliminating the need to hard-code string values throughout. Utilizing these constants allows developers to refer to meaningful names instead of literal string values, thereby increasing the clarity and understanding of the code. This practice also minimizes the risk of typos or inconsistencies that might occur if string values were repeatedly written out in different parts of the code, promoting a more centralized and error-free approach. The function plotnum stocks is designed to create a visual representation of the number of stocks available at each time step based on the provided stock prices data. It takes 2 parameters of prices, a pandas data frame containing the stock prices data, and fixa is optional, a tuple specifying the size of the plot. To achieve this, the function first creates a new figure and axis object using matplotlib. It then calculates the number of stocks available for each time step by checking for non-missing values, non-net and values in each row of the prices data frame. This number is plotted on the axis, with the y-axis representing the number of stocks and the x-axis representing the time steps. The function sets the y-axis label as number of stocks and adjusts the padding of the figure to ensure all elements fit properly. Additionally, it saves the generated plot as an CG file using the provided file path and title. Finally, the function returns the figure object. This code is useful for visualizing the availability of stock data at each time step, aiding in understanding the completeness of the dataset and analyzing trends in the number of available stocks over time. It enables users to efficiently generate and save this plot for further analysis or reporting. The code in question is likely designed to generate a plot that illustrates the number of stocks included in the dataset daily pre-sort over time. In this plot, the x-axis would represent time, while the y-axis would represent the number of stocks available each day in the dataset. The purpose of visualizing this information is to observe the fluctuations in stock availability over time. This can aid in assessing the completeness and consistency of the dataset, as well as in identifying any patterns or anomalies in the availability of stock data. Such insights are valuable for ensuring the robustness of subsequent analyses that depend on this dataset. The code defines a function called plot_all_stock_traces that generates a plot to visualize the cumulative return for all stocks provided in the input dataset. The function accepts three input parameters: returns, which is a pandas data frame containing stock returns data with stock values in columns and time steps in rows; plogy, a Boolean parameter specifying whether to use a logarithmic scale on the y-axis; and figsizer, a tuple representing the figure size, to generate the plot. The code first calculates the cumulative returns for each stock by taking the cumulative product of returns over time and then computes the mean of these cumulative stock returns. It sets up the plot with a title, axis labels, and appropriate styling, plotting the cumulative returns for each stock in blue with a transparency level of 0.1. The mean cumulative return is then overlaid in red. Additionally, a dashed black line is added at sign 1 to distinguish between regions of loss and gain. The output includes saving the generated plot as an CG file titled normalized cumulative stock returns and returning the matplotlib figure object. This visualization tool is useful for comparing cumulative stock returns across different stocks over time, helping to understand overall trends and mean performance relative to individual stocks. The log scale option is particularly advantageous for visualizing data with a wide range of values, making this function essential for analyzing and presenting historical stock return data in a consolidated and comprehensive manner, aiding in investment decision-making processes. This code likely calls a function named plot_all_stock_traces, using daily returnStorg as the input for the returns parameter while setting the logi parameter to true. The function probably generates a plot that displays the traces of multiple stock returns over a period of time. Setting log to true means the y-axis of the plot is shown in a logarithmic scale, which is beneficial for visualizing data with a wide range of values, such as financial data. The primary purpose of this code is to visualize the daily stock returns of multiple stocks simultaneously in a clear and meaningful way. By using logarithmic scaling on the stock traces, the plot facilitates the comparison of the relative performance of different stocks. This approach is particularly useful because, in linear scale plots, extreme values in some stocks can be visually overwhelming, making it hard to discern meaningful trends and comparisons. The function plot_comparatraces is designed to generate a comprehensive plot with multiple subplots, which are used to compare the portfolio values for various types of portfolios. It accepts several parameters at portable, a data frame containing portfolio values numstocks, indicating the number of stocks in the portfolio's test name, the name of the test being conducted. Compare pairs, a list of tuple pairs representing the portfolio types to be compared. And figsize, determining the size of the figure. Upon invocation, the function initiates the creation of a new plot that includes subplots corresponding to the number of pairs specified in the shown_per_pairs list. It iterates over each pair, retrieves the relevant portfolio values from the data frame, computes the portfolio value ratio, and plots these values. Each subplot is then given appropriate titles, styling, and a grid to enhance readability and aesthetics. Furthermore, the function saves the resulting plot as an CG file. The file name for this file is uniquely generated using the test name and the number of stocks involved. The primary purpose of this function is to facilitate a visual comparison of the performance of different portfolios under varying scenarios. By graphically representing the portfolio value ratios for distinct pairs of portfolio types, it allows for easier analysis and interpretation, aiding in decision-making based on the visualized results. The function plotCompareStats is designed to create a grid of box plots for comparing statistics across different portfolio types. It accepts various parameters, including a data frame of portfolio statistics, the name of the statistic to compare, the test name, the number of trials, and the order of portfolio types. Using these inputs, the function generates a grid of box plots that visually compare the specified statistic across the different portfolio types. The primary aim of the function is to facilitate the visualization and comparison of how various portfolio types perform based on selected statistics. By placing box plots side by side, the function allows for a clear view of the distribution of values, median, quartiles, and potential outliers for each portfolio type. Such visualization is crucial for comparing the performance of different strategies and aids in making informed, data-driven decisions. The function employs Seabornsons to generate the grid of subplots and to plot the box plots within them. It customizes the plot by rotating the x-axis labels, setting titles, adjusting the y-axis format for specific statistics, and saving the final plot to a file for further use. This code is particularly useful for analysts and researchers who need to compare the performance of different portfolio strategies based on various metrics. By providing a clear visual representation, the function helps in understanding the differential performance of strategies and identifying the ones that are more effective under specific conditions. The function plotCompareStats accepts a data frame called GitFStats containing portfolio statistics as well as parameters such as test names, numstocks, numtricles, and a specific order for portfolio types. Its primary goal is to produce a visual comparison of statistics across different portfolio classifications through a grid of box plots. Initially, the function selects the relevant names of the statistics to be plotted and prepares the data frame by transforming it accordingly. It then filters the data based on the given number of stocks. Subsequently, the function creates a grid of subplots using Seaborn's facet grid, where each subplot contains a box plot that displays the comparison according to the specified order of portfolio types. Titles, labels, grid lines, and pertinent formatting are set for each subplot based on the specific statistics being presented. Finally, the plot, complete with a comprehensive title, is saved to a file. This function is crucial for visually comparing the performance metrics of various portfolio types. By detailing the portfolio performance across multiple metrics, it aids in thorough analysis and informed, data-driven decision-making. The GeoMean function calculates the geometric mean of a portfolio's value over a period of time using a pandas series, a portfol, which represents the portfolio values at each time step. To compute the geometric mean, the function first divides the value at the end of the period portfol ilo1 by the value at the beginning of the period portfol ilo0. It then raises the result to the power of 1 divided by the length of portfols, effectively taking the nth root of the result, wherein is the total number of values in the portfolio series. Geometric mean is particularly valuable in finance as it represents the average rate of return of an investment over multiple periods. Accounting for the effects of compounding, this makes it more suitable than the arithmetic mean for data series that show exponential growth, such as financial data. By simplifying the calculation of the geometric mean for a given portfolio value series, this function helps in accurately assessing investment performance over time. This Python function, statistics, computes various statistics for a time series dataset representing the values of a stock portfolio over time. The function performs several key calculations. It calculates the one-period returns for the portfolio values, computes the fraction of months that have losses, and determines the arithmetic mean and standard deviation for these one-period returns. Additionally, it calculates the Sharpe ratio using the derived arithmetic mean and standard deviation. The function creates a dictionary containing essential statistics, including the number of data points in the portfolio values, the final value of the portfolio, and the mean value of cash holdings. It also includes the arithmetic mean of the one-period returns, the geometric mean of portfolio values, the standard deviation of the one-period returns, the Sharpe ratio, the maximum drawdown, the maximum pull-up within a specified window, and the fraction of months with losses. These statistics provide crucial insights into the performance and risk of the portfolio over time. Notably, the Sharpe ratio serves as a measure of risk-adjusted return, helping investors assess the return of an investment relative to its risk. We use this code to analyze and evaluate the historical performance of a stock portfolio. This analysis aids investors in making informed decisions about their investment strategies and optimizing their portfolio allocations. The function adjust_weight is designed to optimize portfolio weights by minimizing the correlation between assets. It takes in the historical returns of the assets and the current portfolio weights as inputs. The function provides various methods for adjusting weights, including using correlations from all data, a rolling window, pure noise, or equal correlations. Initially, the function validates the inputs and computes the correlation matrix based on the chosen correlation type. It then uses the diversify, adjust weights function at each time step to adjust the portfolio weights by taking into account the correlation matrix, thereby reducing exposure to highly correlated assets. The motivation behind this function is the critical role of diversification in portfolio management. By minimizing asset correlations, the function helps decrease the overall risk of the portfolio, as uncorrelated assets generally move independently. Therefore, adjusting weights based on correlation can lead to a more balanced and less risky portfolio. This tool is particularly valuable for simulation and research purposes, allowing users to explore various strategies for correlation adjustment. This code creates multiple partial function instances by fixing some of the arguments of the function adjust_weights for different correlation types. For example, Schwantage is set to use correlations for the entire time series by fixing the Shor type argument to all. Similarly, Schwantage will use the last 10 days correlation as naive forecasting by setting Jor type to window and Jor window to 10. The function Schwantage heavy noise applies the actual future 10-day correlations with heavy noise by setting Jor type to window, core window to 10, and Jor noise ASL to 0, 5. In another instance, the Schwantage pure noise sets the correlations to pure noise by setting Jor type to pure noise. Meanwhile, Schwantage equal uses correlations that are all equal by setting Jor type to equal and Jor equals to 0, 1. Finally, Schwantage inverts the actual future 10-day correlations by specifying Jor type as window, core window as 10, and Jor invert as true. Using these partial functions allows pre-configured versions of the adjust_weights function to be available with specific correlation types and parameters. This makes it easier to reuse them in different parts of the code without needing to specify the same arguments each time. It provides a convenient way to handle different scenarios, promoting code reusability and maintainability. The Python function named portfoliohold calculates the cumulative returns for a buy-hold portfolio strategy. It takes a pandas data frame called returns as input, where rows represent time steps and columns represent assets. To calculate the cumulative returns, the function first calls the jumprot method on the input data frame, which computes the cumulative product of each column along the rows. The resulting data frame contains cumulative returns for each asset over time. Next, the function uses the immean method with taxonomy to calculate the average return across all assets at each time step. This means that for each row in the cumulative returns data frame, the function computes the average return across all assets. Finally, it returns a pandas series that represents the cumulative returns for the portfolio over time. This code is beneficial for analyzing the performance of a buy and hold strategy for a portfolio of assets over time. It helps in understanding how the portfolio value changes with respect to the initial investment and allows for comparison with alternative strategies. The code defines a function called portfolioable that calculates the cumulative returns for a rebalanced portfolio. This function takes a pandas data frame as its input, where the rows represent time steps and the columns represent assets along with their respective returns. To determine the rebalanced portfolio returns, the function first computes the mean return for each time step by averaging the values across each row, ignoring any missing data. Next, it calculates the cumulative product of these mean returns, which effectively shows the overall growth of the portfolio over time. This function proves useful for analyzing a portfolio's performance that undergoes periodic rebalancing and where assets are adjusted to maintain target weights. By examining the cumulative returns, portfolio managers and investors can gain insights into how the portfolio has evolved over time. Considering asset allocations and returns, this information is crucial for evaluating the effectiveness of an investment strategy and making informed decisions. The Python function portfolio calculates the cumulative returns for a rebalanced portfolio. It takes 3 arguments to returns a pandas data frame containing asset returns over different time steps. The max weight, the maximum weight allowed for any asset in the portfolio. And Fundadjustor, a function that adjusts the weights to minimize correlations among the assets. Initially, the function sets equal weights for each asset by copying their returns data frame and assigning max weight to all elements. These weights are then adjusted using Fundadjustor to minimize the correlations among the assets. Post-adjustment, the weights are clipped at the upper limit specified by max weight to ensure they do not exceed this value. The weights are then normalized so they sum up to a maximum of 1. Considering any residual cash, the function calculates the cumulative portfolio returns based on these normalized weights and the returns using a weighted returns function. Finally, it returns a pandas series containing the cumulative portfolio returns and the cash component in the portfolio. In summary, this function is essential for rebalancing a portfolio to optimize returns and manage risk by minimizing asset correlations and ensuring effective diversification. The code defines a function called portfoliothres that calculates the cumulative returns for a portfolio strategy based on a threshold criterion. Initially, it determines the asset weights by evaluating if the future returns for each asset exceed a specified threshold min return. It assigns a weight max weight to assets that meet this criterion. Following this, the asset weights are normalized to ensure that their sum does not exceed 1. Next, the function calculates the cumulative portfolio returns by using the normalized asset weights and accounting for any uninvested cash if the sum of the weights is less than 1. This is achieved by calculating the weighted sum of asset returns to determine the overall portfolio return. Finally, the function returns the cumulative portfolio returns and any uninvested cash as a pandas series. This code is particularly useful for investors or analysts aiming to implement a portfolio strategy that emphasizes assets with future returns above a certain threshold. It aids in diversifying the portfolio by selecting assets based on this specific criterion and allows for tracking the performance of such a strategy over time. The function portfolioadapt calculates the cumulative returns for an adaptive portfolio by leveraging historical returns, future return expectations, and asset weight limits. It begins by mapping future returns to asset weights through a linear mapping based on provided thresholds and weight limits. If a correlation adjustment function is provided, the function adjusts the asset weights to minimize their correlation. The asset weights are then clipped to their upper limit and normalized to ensure they sum up to 1. Ultimately, the function calculates the cumulative portfolio returns based on these weighted returns and cash holdings. This approach allows for the construction of an adaptive portfolio that dynamically adjusts asset weights according to future return expectations, aiming to achieve better performance by investing more in assets with higher expected returns. The optional correlation adjustment feature further enables portfolio customization to align with investor preferences or risk appetite. The function SimToNetTrial is designed to perform a single simulation trial for various portfolio types utilizing given parameters and data. It takes parameters such as the trial number, the number of stocks, historical returns data, future returns data, and several configuration options for different portfolio strategies. Initially, the function randomly selects a subset of stock tickers based on the specified number of stocks. It then filters the historical and future returns data for these selected stock tickers to ensure they have common periods with available data. Subsequently, noise can be optionally added to the future long-term stock returns based on a specified scale to mimic real-world uncertainties. Once the data preparation is complete, SimToNetTrial proceeds to simulate different portfolio types including buy hold, rebalanced, threshold, and adaptive, among others, depending on the provided configuration settings. Throughout the process, the function logs the performance statistics, portfolio values, and index values for each type of portfolio. Finally, it returns the gathered statistics, portfolio values, and index values from the simulation trial. The modular nature of SimToNetTrial allows it to serve as a foundation for higher-level functions such as SimManyTrials, which likely coordinates multiple simulations across different trials and aggregates the results. This modular approach contributes to a more organized and maintainable code structure. The code defines a function named SimManyTrials that performs numerous simulations of different portfolio types by randomly selecting stock tickers for each trial. This function accepts three main parameters: numStocks, which indicates the number of random stocks in the portfolios either as an integer or a list; numTrickles, representing the number of trials to conduct; and QUARGs, which encompasses other keyword arguments passed to the function SIMUNETRICLES. First, the function ensures that numStocks is formatted as a list and initializes lists to store the results. It then iterates over each portfolio size specified in numStocks, ensuring that the specified number of portfolio stocks is valid based on external data, namely TALTICRST. A partial function, using functools, partial, is created to fix arguments for parallel execution, addressing the limitation that the parallel system cannot handle extra arguments directly. The core simulation function, SIMUNETRICLE, is executed in parallel using the multiprocessing module, which uses a specified number of processes to manage parallel execution. The results of these trials are then unpacked and stored in separate lists for statistics, portfolio values, and the trial index. These lists are subsequently combined into pandas data frames, facilitating easier manipulation and analysis. The function ultimately returns two pandas data frames: EDFASTATST, which contains statistics for all trials, and JITFPortVol, capturing all the portfolio traces. Overall, this code aims to automate and parallelize the simulation of different portfolio configurations, thereby increasing the efficiency of the simulation process, particularly when handling a large number of trials or portfolio configurations. The resulting data frames offer a structured approach to efficiently analyze the simulated portfolio data. The SimPlotAll function is designed to simulate random portfolios and plot their resulting statistics. The function takes several input parameters: test name, a string indicating the name of the test; numStocks, a list of integers representing the number of stocks in the portfolios; numTrickles, the number of trials with random portfolios; comparePairs, a list of tuple pairs for comparing different types of portfolios in the plots; order, a list dictating the order of portfolio types; and additional arguments passed through QUARGs. The function first utilizes SIMUNETRICLES to perform the portfolio simulations based on the provided parameters. Once the simulations are complete, it plots comparisons of the portfolio traces for each number of stocks in numStocks using plotCompareTraces. This enables the visualization of how different portfolios perform over time. Next, it defines a list of performance statistics to be compared, such as average arithmetic return, geometric mean, standard deviation, Sharpe ratio, mean cash, maximum drawdown, maximum pull-up, and months of loss. It then uses plotCompareStatStone to plot comparisons of these performance statistics for the simulated portfolios. This aids in analyzing and comparing the performance of different portfolios based on these metrics. Overall, the SimPlotAll function helps in conducting simulations, analyzing the performance of random portfolios, and comparing different portfolio types. It streamlines the process of running simulations and visualizing the results, thereby facilitating better decision-making in investment strategies. The Python function gnormalDiff generates the probability density function diff for a normal distribution using specified mean and standard deviation parameters, and also prepares a corresponding label for plotting. This function takes four parameters: an array of floats dex for which the pdiff is calculated, the mean of the normal distribution, the just standard deviation of the normal distribution, and a name string to prepend to the label. Within the function, it calculates the pdiff values using the norm pdiff function from the SysAPI stat module based on the provided mean and standard deviation. Then, it calls another function, normalProbLoss, to calculate the probability of loss using the given mean and standard deviation. After that, it constructs a label that includes the name, mean, standard deviation, and the computed probability of loss intended for use in plotting. The function returns a tuple containing two elements: a numpy array with the calculated pdiff values and a string label for plotting. This encapsulated approach facilitates generating pdiff values for normal distributions and creating descriptive labels, easing the visualization and analysis of data distributions in statistical and data analysis tasks. The function plotCompareNormals is designed to compare two normal distributions by taking parameters such as their means, standard deviations, names, and other optional visualization settings. It generates a plot that visually compares the probability of loss for each distribution and the probability that the first distribution is less than the second. The function proceeds by creating subplots for each set of mean and standard deviation values provided. generating a range of equivalues to plot the distributions, and calculating and plotting the probability density functions PDIFs for both normal distributions. Additionally, the function calculates the probability that the first distribution is less than the second. Displaying this probability in the title of the subplot, it includes a vertical line at K0 to visually separate gains and losses. To enhance the plot's readability, it adjusts the appearance by hiding y-axis numbers, showing percentage numbers on the x-axis and setting the x-axis label. If a file name is provided, the function saves the plots to disk. Overall, the PlotcomparNormalist offers a straightforward way to visually compare different normal distributions, making it a valuable tool for analyzing and understanding the characteristics of various datasets or random variables. The code in question generates a comparison plot of two normal distributions representing different assets. Labeled as Asset A and Asset B, it specifies the means and standard deviations for these distributions and assigns appropriate names to the assets. The resulting plot is saved as an SIG file named variance is not risk-a-B comparison. SIG. This graphical representation is useful for visually comparing the distributions of different assets, making it easier to observe differences in their means and variances. Such visual tools can aid in investment decisions, risk analysis, or other scenarios where data representation is beneficial. The function plotNormalPDIF generates a visual representation of the normal distribution using the specified mean and standard deviation. It accepts parameters such as the mean, standard deviation, a matplotlib object tax, x-axis label hucklabo, plot title, x-axis range husmind and husmax, and an optional boolean to determine whether to plot a dashed line at the mean. The function first generates two arrays of equivalues second and hextooth, each containing 100 values within the given x-axis range, split at the mean value 0. It calculates the corresponding I-values using the norm PDIF function from NumPy. The area under the curve is filled with red for losses, negative values, and green for gains, positive values using the fill-between method. If the dashed line mean parameter is true, a vertical dashed line representing the mean is added to the plot. Additionally, a vertical line at K0 is included to clearly separate gains from losses. The function sets the x-axis label and formats it to display percentages, while the y-axis tick labels are hidden to keep the focus on the plot itself. The probability of loss is calculated using a separate function NormalProbLoss, not shown in the code and included in the plot title. Alongside the mean and standard deviation values, the title is updated based on the inputs and set for the plot. Overall, this function enables the efficient creation of plots that illustrate the normal distribution for a given set of parameters. Highlighting areas of gains and losses, it offers a practical tool for visualizing the probability distribution of data, making it useful in fields like finance, statistics, and data analysis where understanding data distribution is critical. The code defines a function called plotNormalPDIF designed for plotting one or more normal distributions based on specified means and standard deviations. This function can handle both single and multiple distributions at once. Offering flexibility in visualizing data, the function accepts several parameters including ymean, which can be a float or a list of floats, as either a float or a list of floats, xmin lower x-axis bound, pixmext upper x-axis bound, xfelaname for saving the plot, and xfixsize the size of the figure. If the ymean parameter is not a list, the function generates a single plot using the provided mean and standard deviation. Conversely, if the mean is a list, employing multiple distributions, subplots are created for each mean value in the list. For each plot, the function calls an internal plotNormalPDIF function to draw the normal distribution curve. After plotting, it adjusts the padding and, if a filename is specified, saves the resulting figure to the disk. This code is particularly useful for visualizing normal distributions with different parameters. Aiding in the understanding of data distribution, the ability to plot multiple distributions simultaneously is advantageous for comparison and analysis purposes. By encapsulating the plotting logic, the function remains reusable and customizable for a variety of scenarios. The code snippet appears to plot a normal probability density function key for a set of standard deviations. This plotNormalPDIF function, likely a custom-built function, generates a visualization of a normal distribution with a specified mean and standard deviations. In this example, the mean is consistently set at d0, 1 across all data points, while the standard deviations are given as a list 0, 1. 0, 5, 0, 1, 0, 2. The function creates a plot based on these parameters and saves it as an CG file named variance is not risk probability of loss 1. CIV. This code is particularly useful for visualizing the PTF of a normal distribution with varying standard deviations, aiding in understanding the dataset's distribution or performing statistical analysis. By providing a graphical representation, it simplifies the interpretation of the data's characteristics. The code provided is designed to create a plot of a normal probability density function for a random variable with a specified mean and standard deviation. In this instance, the mean is set to 0, 1 for 4 different variables. Although the standard deviation is not included in the snippet, once generated, the plot is saved as an CG image file named variance is not risk probability of loss 2. CIV. The function plot normal diff presumably takes parameters for the mean, standard deviation, and the file name to save the resulting plot as an CG image. The generated graph visualizes the probability distribution of the normal random variable characterized by the provided mean and standard deviation. This visualization aids in understanding the distribution characteristics and associated probabilities, which is particularly useful in statistical analysis, finance, and other fields where comprehending data distribution is essential. The function compare_prob_loss is designed to visualize and compare the probability of loss for two normally distributed random variables. It accepts mean values to mean on and mean to an array of standard deviations ist, an optional file name for saving the plot, and a figure size as input arguments. This function utilizes the matplotlib library to create a plot that shows the comparison of probability of loss for the two distributions. It operates by calculating the probability of loss for each mean value using the helper function normal_prob_loss, and then plotting these probabilities against the different standard deviations provided in the SHEST array. The plot is enhanced with legends, titles, axis labels, and appropriate formatting. If a file name is provided, the function saves the plot to this specified file. Ultimately, the function returns the generated matplotlib figure object. This visualization tool is particularly useful when comparing the probability of loss between two different normal distributions given their mean values and standard deviations, aiding in the understanding and risk assessment of the random variables described by these distributions. The code likely generates a plot comparing the probability of loss between two sets of data distributions with varying standard deviation values. Initially, it defines a file name where the plot will be saved. It then creates an array of standard deviation values with finer steps near 0, which is crucial for a detailed comparison of standard deviations ranging from 0, 1 up to 1, 0. The array of standard deviation values is ensured to be unique and sorted in ascending order. The function compare_prob_loss is then called with parameters mean in 0, 1, mean to 0, 1, stst, and file name, which presumably generates a plot comparing the probability of loss based on the provided mean and standard deviation values. This visualization is essential for understanding how the probability of loss changes with different standard deviations for the two sets of data distributions described by meanton and meanto. It helps in comprehending the impact of variability measured by standard deviation on the likelihood of incurring losses in the data. The code defines a function, ist_weighted sum, that calculates the standard deviation of a weighted sum of correlated random variables. It takes three inputs: an array of weights for the random variables, an array of their standard deviations, and a matrix of correlations among them. The function computes the standard deviation by iterating over each pair of weights, multiplying the weights, their standard deviations, and the correlation between each pair. Then summing up these results, it ultimately returns the square root of the calculated sum as the standard deviation of the weighted sum. The calculation involves two nested loops to iterate over pairs of random variables, multiplying and summing as described, which makes this operation computationally intensive. A note in the code suggests optimizing this part for performance, especially for large datasets, as nested loops can be inefficient. This capability is essential in fields such as finance, risk management, and statistical modeling, where understanding the overall risk and diversification benefits in a portfolio or system is crucial. The provided code offers an efficient method for calculating this important measure. The code defines a function named means_to_assets that computes the mean and standard deviation for various weighted combinations of two assets. It accepts four parameters: a mean, an array of the assets' means, USD, an array of their standard deviations for a matrix denoting the correlation between the assets. And step, a float indicating the increment for the weights with a default value of 0. 1. Initially, the function validates the input parameters to ensure they possess the correct dimensions. Following this, it initializes lists to hold the calculated means, standard deviations, and weights for the different combinations of asset weights ranging from 0 to 1, 0, iterated by the specified step size for each combination of weights. The function calculates the mean and standard deviation of the weighted sum of the two assets utilizing the provided parameters. These values, along with the corresponding weights, are stored in the initialized lists. Upon completion, the function returns three NumPy arrays, one containing the calculated means, another with the standard deviations, and the third listing the weights used in each calculation. This function is instrumental in analyzing a portfolio composed of two assets by computing the mean and standard deviation for different weight allocations. Such analysis is vital in portfolio optimization and risk management within finance, as it aids in understanding the variations in a portfolio's risk and return based on different asset weightings. This function creates a 4-subplot figure to analyze combinations of two assets by taking the mean, standard deviation and correlation matrix of the two assets along with their names. In the first subplot, it displays the mean and standard deviation for all weighted combinations of the assets, distinguishing positive means in green and negative means in red. It also includes the original mean and standard deviation of the assets as black dots, shows the minimum risk portfolio with a dashed black line, and prints out its weights. The second subplot presents the normal distribution for the minimum risk portfolio and calculates the probability of loss for this portfolio. The third subplot displays the normal distribution for asset A, while the fourth subplot shows the normal distribution for asset B. The function relies on auxiliary methods such as plotNormalDiff for plotting normal distributions and other utility functions for calculations. The resulting figure can be optionally saved to a file if a file name parameter is provided. This code serves as a tool for visualizing and analyzing the risk and return characteristics of different combinations of two assets, assisting investors and analysts in making informed decisions when constructing portfolios. The provided code snippet sets up data to plot a graph illustrating the risk and return characteristics of a portfolio invested in two assets, referred to as Asset A and Asset B. It includes the mean average return and standard deviation risk for each asset, along with the specified correlation coefficient between them. This data is then used by the function plotAssets to generate a plot that visualizes the relationship between risk and return in a portfolio composed of these two assets. The purpose of using this code is to visually comprehend the trade-off between risk and return when investing in different assets. By plotting data points that represent each asset and their interrelationship gauged by their correlation, investors can make better informed decisions regarding portfolio diversification and risk management. This visual representation aids in understanding how combining these assets might influence the overall risk and return profile of the portfolio. This Python code snippet declares and assigns string constants to specific names. Representing titles are labels and plots are data analysis applications. Using constants instead of hardcoding these names ensures consistency and simplifies future updates or changes. The constant window length is used to represent the window length in the context of analysis or plotting. Mean return serves as the title or label for mean daily return in plots, whilst return is used for standard deviation of daily return. The constant core denotes the title or label for correlation in plots. And ticker 2 represents a modified ticker name, potentially a combination of the original ticker name ticker with an added suffix or prefix to. Finally, ticker pair is used to label ticker pairs in analysis or plotting. By defining these constants, the code becomes more readable, maintainable, and easier to refactor if needed, avoiding the scattering of strings throughout the codebase. The function shall_rolling_stats is designed to compute rolling statistics for stock returns based on specified window lengths. It takes three parameters: returns, which is a pandas data frame containing stock returns; tickers, a list of stock tickers; and windows, a list of integers representing the lengths of the rolling windows. Initially, the function generates a list of unique combinations of stock tickers and creates labels for each window length to be used in plotting. It then extracts the stock returns data for the specified tickers from the input data frame and initializes lists to store the calculated rolling mean. rolling standard deviation, and rolling correlation for each window length provided. The function calculates the rolling mean, standard deviation, and correlation for the stock returns and stores these results in their respective lists. The lists of results are then converted into pandas data frames, which can be used for visualization purposes. The data is reshaped to make it compatible with Seaborn for plotting. Utilizing the mount function, the function also combines the ticker columns into a single column for correlation data and filters the data to include only relevant ticker pairs. Finally, it converts the correlation data into a format suitable for Seaborn visualization. The function returns the calculated rolling mean, rolling standard deviation, and rolling correlation as pandas data frames. Overall, the function is valuable for analyzing the historical performance of stocks, offering insights into how key statistics like mean, standard deviation, and correlation evolve over different rolling time intervals, and facilitating easy comparison and visualization across various stocks and periods. The code defines a function, tplot_rolling_stats, which creates visualizations of rolling statistics for multiple stock tickers or pairs of tickers using Matplotlib and Seaborn libraries. The function takes several parameters, a data frame each containing the data, the name of the statistic is .name to plot, a list of stock tickers tickers, a list of window lengths windows, the column main used to differentiate between rows ticker, and an optional horizontal line value she-lines. Using Seaborn, the function generates subplots for each ticker or ticker pair, displaying the rolling statistics as line plots. If a t-line value is provided, it adds a horizontal black dashed line at that specified value in each subplot to indicate a reference level. The function adjusts the padding of the plot and saves it as an SIGI file, incorporating the ticker names and window lengths into the file name. Additionally, the function returns the Matplotlib access object for further manipulation or display. This function is crucial for visualizing trends of rolling statistics across multiple stock tickers, facilitating an easier comparison and analysis of data. It helps in identifying patterns, trends, and relationships among different assets over time, which can be pivotal for making informed investment decisions or analyzing portfolio performance. The code defines a function called tplot_rolling_stats, which is used to compute and visualize rolling statistics such as mean return, standard deviation, and correlation from a given set of return data for different stocks over various time windows. The function requires 3 parameters: returns, which is a pandas data frame containing return data for various stocks, tickers, which is a list of strings representing the stock tickers, and windows, a list of integers representing the window lengths for calculating the rolling statistics. Initially, the function calculates these rolling statistics mean, standard deviation, and correlation by invoking another function, cal_rolling_stats. The calculated statistics are then stored in the variables shitmean, didfster, and shitforge. Following this, the function proceeds to plot these statistics by calling 3 other functions responsible for plotting rolling mean, rolling standard deviation, and rolling correlations respectively. When plotting the mean return, the function adds a line at the value 1, 0. For the standard deviation, it plots a line at the value 0, 0, and similarly for the correlation, a line at the value 0, 0 is plotted. This approach is beneficial for analyzing the performance and dynamics of different stocks over time. Visualizing rolling statistics provides insights into trends, volatility, and correlations between stocks within specified time windows. Such analysis aids in making informed investment decisions and devising risk management strategies based on historical data. The code appears to calculate and plot rolling statistics for stock returns using specified tickers and window sizes. The function tplot_rolling_stats likely takes in the following parameters: returns, which contains daily returns data for stocks, tickers, a list of stock tickers for which the rolling statistics are calculated, and windows, a list of window sizes such as 20, 60, and 250 for the rolling statistics calculation. The purpose of this code is likely to analyze the performance of the given stocks by calculating rolling statistics, such as the rolling mean, rolling standard deviation, or other metrics. By plotting these rolling statistics, one can visualize the trends and patterns in the stock returns over time. Utilizing different rolling windows in this analysis provides a comprehensive perspective on stock returns, helping to identify trends, assess volatility, and evaluate potential investment opportunities or risks associated with the selected stocks. The code defines a function, blub_Celsius_return, designed to create a comparison plot between the sales valuation ratio of a stock and its future daily and long-term returns over a typical investment period of 2-3 years. Initially, the function extracts sales ratios, daily returns, and future long-term returns from the provided datasets and converts the annualized long-term returns to daily returns. The data is organized into a pandas data frame, with any rows containing missing values removed to ensure data integrity. Subsequently, the function generates a new figure containing 3 subplots for various comparisons. It plots sales versus long-term returns and sales versus daily returns in separate subplots, and then displays sales versus both daily and long-term returns together in a third subplot. Axis labels, ticks, and padding are adjusted to enhance visualization clarity. Finally, the generated plot is saved as an CSV file, facilitating further analysis or reporting. The main goal of this code is to visually evaluate the relationship between a stock's sales ratio and its future returns, both daily and long-term. This analysis can assist investors and analysts in understanding how the sales ratio might predict future stock performance over different time horizons. Such visualizations allow for insights that numerical data alone may not reveal, thereby aiding in decision-making processes related to buying or selling stocks based on valuation metrics like the sales ratio. This function generates a scatter plot to compare the quarterly percentage change in stock price sales of a given stock ticker with its quarterly return. On the scatter plot, the x-axis represents the percentage change in stock price, whereas the y-axis represents the quarterly return. By visually plotting these two metrics against each other, one can observe any potential relationships or patterns between stock price changes and returns over time. This visualization aids investors in making informed decisions based on historical data and trends. By examining how stock price changes impact returns and identifying any correlations, the scatter plot can help analyze stock performance and reveal potential investment opportunities. The function in question is designed to plot the relationship between product sales and return rate for a specified ticker symbol. With full used as an example, the code retrieves the necessary data for the given ticker from a dataset or API, calculates the sales and return values, and then plots these values on a graph to visualize any potential correlations or patterns. By examining this relationship, analysts or decision makers can gain insights into how changes in sales might impact returns, or vice versa, aiding in future business decisions and strategies. This code proves useful for financial analysts, companies, or investors seeking to analyze the relationship between sales and returns for a specific financial instrument. The code in question generates a plot to illustrate the relationship between the sales performance and the returns of the stock with the ticker symbol BBs. The function blub_Celsius_return retrieves and combines the necessary data for the specified stock, and then plots this data to potentially reveal any correlation or patterns between sales performance and stock returns. This analysis can offer valuable insights into how a company's financial health and performance may influence its stock price movements. By visualizing this relationship, investors and analysts can make more informed decisions regarding whether to buy, sell, or hold the stock. It aids in identifying trends, correlations, and patterns that are crucial for making sound investment choices. The function SimPlotRandom walks is designed to simulate and plot two types of stock price movements: random walks and semi-random walks, based on daily stock returns. In the random walk scenario, daily stock returns are generated using a normal distribution with mean and standard deviation derived from actual stock returns. This approach can produce a wide range of simulated share prices, potentially leading to unrealistic representations of actual behavior. Conversely, in the semi-random walk scenario, while the daily returns are still normally distributed based on the actual return's standard deviation, the means are calculated differently. Here, the mean is derived from the last simulated stock price and the projected future stock price, resulting in simulations that exhibit random walks over the short term but do not stray significantly from the actual stock price over the long term. The code employs NumPy and Pandas for handling data structures, generating random numbers, and creating data frames, while Matplotlib is utilized to visualize both simulated and actual stock prices. The function takes several parameters, including the stock ticker, daily returns, years to project forward, number of simulation trials, and the figure size, ultimately returning a Matplotlib figure object. This function can be used to simulate various scenarios of stock price movements based on random and semi-random processes. Such simulations are pivotal in understanding potential future stock price trends and the impact of different prediction methodologies. The resulting visualizations offer valuable insights into stock price dynamics, highlighting the importance of balancing short-term randomness with long-term trends in stock investment strategies. The code calls a function named simplotRandomWalks with 3 arguments: a ticker, look ahead, and returns. This function is intended to simulate and plot random walks for stock price movements based on the provided daily returns data. The first argument, the ticker, specifies the stock symbol, for example, BB, for which the random walks will be generated and plotted. The look ahead argument determines how many time steps into the future the simulation will run. The returns argument contains the daily returns data corresponding to the specified stock symbol. The function is likely designed to create multiple random walk simulations using the daily returns data. Then plot these simulations to visualize potential future price movements for the specified stock. Such simulations are useful for understanding potential outcomes and assessing risk in investment or trading scenarios. The given code appears to generate a simulation of random walks based on stock market data. It uses several parameters to conduct this simulation. The ticker parameter is set to full, representing the stock symbol for the company. Under analysis, this specific symbol is necessary to identify which stock's data will be used in the simulation. Another key parameter is look ahead, which is set to 1. This measures how many steps into the future the simulation will predict, indicating that the simulation will project the next step in the stock's price movement. The returns parameter, designated as daily returns, likely refers to historical daily returns data. This data, which might be stored in a pandas data frame or a similar structure, is essential for generating the random walk simulation because it provides a basis for estimating the future movement of stock prices. Overall, the purpose of this code is to simulate the future trajectory of a stock's price by employing historical returns using the random walk model. This financial model helps analysts and traders to gauge potential risks and expected returns associated with a particular stock, aiding in investment decisions. The function call to simplotRandomWalks seems designed to plot a simulation of random walks for a specified stock ticker symbol. In this case, a couple. Each step in the simulation is determined by the provided daily returns data. This look ahead parameter likely specifies the number of steps in advance the simulation should calculate. Random walk simulations are commonly used in finance to model stock price movement based on historical data, where future price changes are influenced by past daily returns. These simulations help in understanding the potential volatility and uncertainty in stock prices. In summary, the function simplotRandomWalks likely generates a plot visualizing possible price paths for the given stock ticker based on historical daily returns data. This assists investors or analysts in assessing the range of potential outcomes and associated risks. The code defines a function named plotLinearFilter designed to generate and visualize a linear filter for creating portfolio weights. This function accepts several parameters: the range of mean returns MUMIN and MUMAX, the maximum weight allowed for the portfolio weight max, the step size for generating points, the color of the plot line, and an optional file name for saving the plot. The function begins by calculating parameters JUT and JB for the linear function y times xb. It then creates 3 segments of this linear function based on the specified ranges of MUMIN and MUMAX. These segments are concatenated to form the complete linear filter. The next step is to plot this linear filter using Matplotlib, followed by adjusting the y-axis and x-axis ticks and labels to ensure readability. Finally, if a file name is provided, the plot is saved to a file. This code is essential for visualizing a linear filter that determines how weights are assigned to different assets in a portfolio based on their mean returns. The resulting plot aids in understanding how the weights change with varying mean returns within the specified range. This visual representation is particularly useful for making informed decisions when constructing a portfolio. The code likely calls a function named plotLinearFilter, passing the file name filterLinear as an argument. This function is probably designed to read and process the contents of the specified CG file to visualize a linear filter. Within this plotLinearFilter function, there is likely code to parse the seed file, extract relevant information such as filter parameters or characteristics, and then plot or visualize this filter in an appropriate format. Such a function is essential for interpreting and visualizing a linear filter represented in an CG file. making it easier to understand its properties or characteristics visually by providing the CT file name to the function. The code permits automated processing and visualization of linear filters stored in CT format, thereby improving the efficiency of analyzing and working with filter data. The code defines a function named LogWeights, which runs an algorithm designed to diversify portfolio weights. This function accepts several parameters: Schweitzer, an array representing the original desired portfolio weights; TOR, a correlation matrix of asset flows; Schweizguess, an array containing initial adjusted portfolio weight guesses; a file name, a string representing the file name for storing results in the C file; and TTOL, a tolerance level that halts the diversification algorithm when adjustments fall below this threshold. In the function, a list called log is initialized to store logs of adjusted weights. The function then calls diversify, adjust weights, another function responsible for adjusting the weights according to the algorithm. This list is converted into a pandas data frame named IDFA, from which percentage changes for each iteration are calculated and saved in another data frame. If a file name is specified, if and TITF are saved as C files in a designated path. Both data frames are then displayed and returned by the function. This function is useful for optimizing and diversifying portfolio weights, allowing users to analyze weight changes over multiple iterations and, if desired, save these results in CE files for further analysis or record keeping. This code snippet appears to be part of a larger program focused on financial calculations or portfolio management, specifically utilizing a function named LogWeights to compute diversified weights for a portfolio. The code first defines an array weights work representing the original weights of two assets in a portfolio, set at 0, 9 and 0, 12. It then creates a correlation matrix score, which details the correlation between the two assets, with 1, 0 denoting self-correlation and 0, 5 representing the correlation between the two assets. Following this, a variable file name is initialized with the value diversify example 0. Lastly, the code calls the LogWeights function with the original weights, the correlation matrix, and the file name as arguments. The intent of this code is to calculate or update asset weights in a portfolio based on the provided correlation matrix. This LogWeights function likely implements a diversification algorithm that adjusts asset weights to achieve a more diversified portfolio by considering the given correlation data. In financial contexts, diversification is crucial for risk reduction by investing across various assets that are not perfectly correlated. This snippet thus seems to be a component of a more extensive system designed to automate the diversification process using the specified correlation matrix. The code appears to utilize a function called LogWeights to perform calculations aimed at diversifying a financial portfolio. Initially, the code sets up an original array of weights, named Schweitzer, and a correlation matrix, referred to as score. The array Schweitzer represents the initial weights assigned to various assets within the portfolio, while the correlation matrix score indicates the relationships between those assets. Subsequently, the function LogWeights is invoked with Schweitzer, score, and a file name as input parameters. It is probable that the function computes adjusted weights for the assets based on these inputs and implements some diversification strategy. The adjusted weights and any other pertinent information are likely logged or saved in a file specified by the file name. Diversify example 1. Such code is critical for portfolio optimization and diversification within financial markets. By leveraging the correlation matrix alongside the original asset weights, the function can determine optimized or diversified weights, which aim to minimize risk and enhance return within the investment portfolio. This, in turn, assists investors in making more informed decisions regarding resource allocation to achieve improved market performance. This code appears to calculate the diversified weights of a portfolio by implementing a logarithmic transformation through the use of a function termed LogWeights. Initially, the original weights of the portfolio are stored in a variable called Schweitzer, while the correlation matrix between the assets is captured in another variable named core. The essence of portfolio diversification is to mitigate risk by distributing investments across various assets whose prices are not perfectly correlated and, therefore, do not move in tandem. By utilizing a logarithmic transformation during the diversification process, the weights of the portfolio assets are adjusted based on their mutual correlations. The LogWeights function likely accepts the original weights and the correlation matrix as inputs, conducting the necessary computations to derive diversified weights. These results might then be saved into a specific file for further analysis or reporting purposes. In summary, the code snippet facilitates the diversification of a portfolio by modifying asset weights in accordance with their correlations, potentially reducing overall risk while adhering to investment objectives. The given code snippet is part of a program designed to calculate and log diversified weights based on the original weights and a correlation matrix. Initially, Schweitzorg is an array containing the original weights of 3 different assets or investments. Alongside this, Schcore is a correlation matrix that indicates the correlation coefficients between these assets. Providing insight into how their returns are interrelated, the code calls the logweights function, passing the original weights Schweitzorgs, the correlation matrix Schcore, and a file name diversify example free as arguments. Within the logweights function, diversification techniques are likely implemented to adjust the asset weights with the aim of decreasing the overall risk of the portfolio while maintaining a target level of return. The function performs calculations to determine a new set of diversified weights based on the provided correlation matrix. Finally, the results are presumably logged in a file named diversify example3. This code serves the purpose of optimizing the portfolio by diversifying the weights of various assets according to their correlations, thereby reducing the overall portfolio risk while striving to maintain the desired return. Such an approach is critical in investment management for establishing a well-balanced and risk-adjusted portfolio. This code snippet is part of a larger program or script that involves financial data manipulation. It creates a NumPy array called Schweitzorg, representing the original weights of different assets, and a correlation matrix Schcore, depicting the correlations between these assets. The code then calls a function named logweights, providing it with the original weights, correlation matrix, and a file name, although the purpose of this function is not explicitly detailed in the given context. It appears to be a custom function defined elsewhere in the codebase. The function named logweights and the arguments passed suggest that it might perform operations related to logging or managing weights based on correlations. Functions like logweights can be crucial for managing and analyzing investment portfolios, asset allocations, risk management, or optimizing investment strategies. By utilizing such custom functions, developers can encapsulate complex operations within manageable modules, thus making the overall program more readable, modular, and easier to maintain. The given Python code snippet is part of a larger program focusing on the diversification of a portfolio. Initially, it defines an array of original weights Schweitzorg representing the proportion of total investment allocated to each asset within the portfolio. It also specifies a correlation matrix Schcore for the assets, capturing the relationships between the assets' price movements. In this matrix, a correlation of 1 indicates a perfect positive correlation, 1 indicates a perfect negative correlation, and 0 indicates no correlation. The code then assigns the file name diversify example5 to the variable file names. Subsequently, it calls the function logweights, passing the original weights, the correlation matrix, and the file name as inputs. The function likely performs calculations or transformations related to portfolio optimization or risk management using the given weights and correlation matrix. The underscore preceding the function call signifies the convention of discarding the return value of the function, as it is not required for subsequent processing in the context of finance and investment management. Such calculations are critical for optimizing portfolios, managing risks, and ensuring sufficient diversification. This code is likely a component of a comprehensive portfolio optimization strategy, aiming to maximize returns while minimizing risks by appropriately allocating assets and considering their correlations. The code appears to be part of a larger program focused on diversifying an investment portfolio. Initially, it defines 2 arrays Schweitzorg and Schweitzkis. The Schweitzorg array represents the original weights of different assets within the portfolio, while Schweitzkis is calculated by negating Schweitzorgs, effectively changing the signs of all elements in the array. This indicates an attempt to alter the original asset weights. A correlation matrix Core is provided, which likely represents the correlation values between different assets in the portfolio. Correlation is crucial in diversification strategies as it shows how assets move in relation to each other, thus aiding in risk management and performance estimation. A function named logweights is then called with the original weights. modified weights, correlation matrix, and a file name as input parameters, although the precise role of this log weights function isn't clear from this snippet. Its purpose may involve logging or recording the weights and their changes. The function could be performing some form of analysis or optimization related to portfolio diversification, potentially calculating risk-adjusted returns, volatility, or optimizing weights based on the correlation matrix. The code might be used to experiment with different asset weightings based on correlations to achieve a more balanced and diversified portfolio. By logging the changes and examining the results, it allows the user to analyze how altering asset weights impacts the overall risk and return profile of the portfolio. In summary, this code snippet seems to be part of a financial analysis or optimization process aimed at improving the risk-return characteristics of an investment portfolio through diversification strategies. The provided code snippet seems to be part of a larger program designed for diversifying investment portfolios. Initially, it defines two NumPy arrays WeightsOrg and WeightsGuess, which appear to represent the original weights of assets and the assumed weights of assets, respectively. Subsequently, it creates a correlation matrix using another NumPy array named Core, likely to capture the correlations between different assets within the portfolio. The variable file name is then set to diversify example 7, following these initializations. The code calls a function named logweights with parameters that include WeightsOrg, WeightsGuess, Core, and file name. This function presumably performs calculations or operations on the given data related to portfolio optimization or diversification. The aim of deploying such a function might be to analyze and optimize a portfolio by taking into account the original weights, assumed weights, and asset correlations. This type of analysis and optimization is commonplace in finance and investment management, as it aids in maximizing returns while effectively managing risks. The provided code snippet appears to calculate log weights based on original weights, guessed weights, and a correlation matrix. The function logweights likely performs numerical computations or optimizations with this information. The variables WeightsOrg and WeightsGuess represent the original and guessed weights, respectively, while Schwar represents the correlation matrix. These are passed to the logweights function along with a file name. Convergence example 1. The code's purpose may be to analyze the convergence behavior of an algorithm or process related to the provided weights and correlations. The computed log weights could be used to track the progress, performance, or stability of an optimization or simulation process, offering insights into the behavior of the system being studied. This code snippet appears to be a segment of a larger program, specifically one that uses a function named logweights. This function is invoked with the parameters original weights WeightsOrg, guessed weights WeightsGuess, and a correlation matrix Core. The purpose of this function, inferred from its name and context, seems related to optimization or convergence analysis. It's likely designed to log or record the provided weights and their correlations into a specified file. The WeightsOrg and WeightsGuess parameters are given as NumPy arrays, suggesting they represent some numerical values. These could be financial weights, scientific parameters, or weights in a machine learning model. The correlation matrix Core reveals the correlations between elements in the weights arrays, indicating that the interdependencies between these weights are crucial to the analysis or optimization process. Logging this information into a file is important for various reasons. It can help record the progression of weight optimization, facilitate comparisons between different weight configurations, and assist in debugging convergence issues in iterative algorithms. Such logging is invaluable for tracking the progress of weight adjustments, analyzing the impact of correlations on the optimization process, and investigating potential convergence issues. Additionally, it supports reproducibility, documentation, and thorough analysis of the optimization process. The code snippet in question seems to set up initial parameters related to weights and correlation values before invoking a function called logweights with these parameters. The overarching purpose of this code appears to be calculating convergence metrics based on the given weights and correlation values. The logweights function is likely involved in financial modeling, statistical analysis, or optimization tasks, where weights and correlations are significant factors. By passing the initial weights and correlations to this function, the main objective is probably to analyze their impact on the convergence of the model or the optimization outcomes. In complex systems or algorithms, understanding convergence behavior is essential to ensure the stability and correctness of calculations. Code like this helps monitor and analyze how the model converges, making it possible to adjust parameters if necessary, thereby ensuring the overall reliability and accuracy of the resulting calculations or predictions. This random weight sort function is designed to generate random weights for a specified number of assets and create a corresponding correlation matrix for these assets. This function allows customization of various parameters, including weight scale, minimum and maximum weight values, and the scale and maximum absolute value for the correlation coefficients. The function follows several key steps. First, it generates random weights for the assets using a normal distribution. The weights are scaled based on a weight scale parameter. Then, it ensures these weights fall within specified minimum and maximum values weight min and weight max by clipping them accordingly. Next, it generates a random correlation matrix also using a normal distribution. This matrix is scaled by a specified parameter and its correlation coefficients are clipped to remain within the range of Uormax to Shormax. To ensure symmetry, the function adds the lower triangular part of the correlation matrix to the transpose of its upper triangular part. Finally, it sets the diagonal elements of the correlation matrix to 1, representing a perfect correlation of each asset with itself. This function is particularly useful in finance or statistical analysis scenarios where random inputs are required to test models or algorithms involving asset weights and correlations. The provided code snippet evaluates the average time required to execute a diversification algorithm across random portfolios of varying sizes. Initially, it defines a list named numAssets, which specifies the number of assets in each portfolio. To ensure accuracy, a minimum number of trials, denoted as mintrials, is established for each portfolio size. An empty list, a numUsage, is set up to record the average execution time of the diversification algorithm for each portfolio size. The code then iterates through each size in the numAssets list. For each size, it performs several steps. It generates random portfolio weights and correlations, applies the diversification algorithm to adjust these weights while measuring the time taken, and ensures that the algorithm runs until at least the minimum number of trials is completed or the total time surpasses a 1 second threshold. The average time per trial is then computed and appended to the numUsage list. The end result is a collection of average times taken to diversify random portfolios of different sizes. This analysis provides insight into the salability and performance of the diversification algorithm, enabling evaluation of its efficiency across various scenarios and informing its practical application in portfolio management. This code snippet uses Matplotlib to generate a line plot. It creates a new figure with a specific size, plots the data time usage as z-axis values against numAssets as x-axis values, sets a title and labels for the axis, adjusts the padding within the figure, and then saves the figure as an CSV file. First, chplot subplot generates a new figure and axis, then hex plot plots the data on the axis. Setting the title and labels provides context to the plot, while shvig tight layout adjusts the spacing to enhance the plot's appearance. Finally, shvig savefig saves the figure to disk as an CSV file. This code is vital for visualizing data using Matplotlib, enabling the creation of high-quality plots for analysis or presentation purposes. It aids in gaining insights into the data and effectively communicating findings. This code snippet generates a series of random portfolios for various numbers of stocks as specified in the numStocks list. For each number of stocks in the list, a fixed number of random portfolios, as indicated by numtrials, were generated for testing. The main objective of this code is to conduct a simulation study that creates random portfolios to examine the impact of the number of stocks on certain metrics or criteria being evaluated. By producing multiple portfolios for each specified number of stocks, the resulting data can be analyzed to determine how the number of stocks in a portfolio affects performance, risk, or other attributes under investigation. Additionally, the COMET provides information on the time required to run this simulation with the given configuration on a specific queue. This information is crucial for estimating the computational resources necessary to execute the simulation successfully. The code in question is measuring the time it takes for a specific function or block of code to execute using the magic command time, which is a feature available in Jupyter Notebooks for CPython. Additionally, the code is running a simulation based on several provided parameters. These parameters include the test name, historical and future returns, the number of stocks, the number of trials, noise scale for future returns, and adjustment function for correlations, as well as minimum and maximum return thresholds and minimum and maximum weights for the simulation. By employing such timing functionality, one can monitor the performance of the simulation code and ascertain the duration it takes to execute. This timing information is crucial for optimizing performance and understanding the computational requirements of the simulation. The code snippet shown utilizes the magic command time to calculate and display the execution time of the subsequent code cell, which appears to focus on performance or timing analysis for a function call related to financial testing or simulation. The function simplotl is called with various parameters including test name, returns, feature returns, num stocks, num trickles, noise oscilla featurettes, funtagestor, min return, max return, min weight, and max weight. This function is likely intended to simulate and plot financial data, potentially for portfolios or investment strategies. Using time here is crucial for measuring the execution time of this specific financial simulation for data until the year 2010. The timing information obtained is essential for optimizing the code, identifying performance bottlenecks, or comparing the efficiency of different implementations. This kind of analysis aids in understanding the computational resource requirements necessary for running such simulations and can be leveraged to enhance the overall performance of the financial analysis process. The given code snippet is designed to measure the execution time of a specific section of the code using the time magic command in Jupyter Notebooks or Python. This command, when placed at the beginning of a cell, records the time taken for the entire cell to execute. After measuring the execution time, the code proceeds to call a function named simplotl with a set of predefined parameters. These parameters include test data from 2010, daily returns, future returns, the number of stocks, the number of trials, the noise scale for future returns, an adjustment function for correlations, and constraints for minimum and maximum returns and weights. Measuring the execution time of code is a useful technique for understanding its performance, identifying bottlenecks, and optimizing it for greater efficiency. By timing code execution, developers can assess the impact of modifications on the speed and overall performance, helping them to make informed decisions about potential improvements. This code segment is designed to time the execution of a function and test a trading strategy by simulating it under various scenarios. It utilizes the simplotl function to perform simulations for a trading strategy under different conditions. Labeling the test as test D, the historical daily returns for the stocks being traded or sorted from the daily returns dataset, while future annualized returns are simulated using the future mean 10 returns data. The portfolio's composition is specified by num stocks, which determines the number of stocks included, and num trickles, which dictates the number of simulation trials. To reflect uncertainty, noise oscilla featurettes 0.5 is introduced, adding noise to future return predictions. A function named adjustWeightsOr is used to adjust portfolio weights based on stock correlations. Defined by the funtagestor parameter, the minimum and maximum desired returns for the strategy are set between min return 0.1 and max return 0.5, while portfolio weight constraints are specified with min weight 0.0 and max weight 0.1 for each stock. Running code like this is vital for quantitatively testing trading strategies, enabling an analysis of potential performance under different conditions by simulating trades based on historical and predicted future returns, incorporating correlations, and imposing constraints on expected returns and portfolio weights. Valuable insights into the strategy's effectiveness and associated risks can be obtained. The timing feature to time is additionally beneficial for measuring the code's performance and the strategy's efficiency in processing data and making decisions. The code defines a dictionary named JADPargs, which contains various parameters for the adaptive robustness tests. The purpose of this code is to store a set of flags or options that can be used within a testing or analysis framework to control different aspects of adaptive testing strategies. For instance, one parameter, CHOMPARPairs, specifies a list of pairs that will be compared during the test, while another parameter, SHORTER, dictates the sequence in which these comparisons are conducted. Additionally, there are several Boolean flags such as JUSUPOLT, JUSITERS, JUSRABLES, and JUSCADAPT, among others, each controlling specific features or behaviors within the adaptive testing framework. Having these parameters stored in a dictionary format allows for easy customization and modification of the testing strategies without the need to alter the underlying code. By simply changing the values within this dictionary, one can effortlessly switch different testing options or behaviors on and off, thereby enhancing the flexibility and adaptability of the testing framework to accommodate various scenarios. The code snippet employs the time magic command, a feature in Jupyter Notebooks designed to measure the execution time of a specific code cell. This particular code cell includes a function call aimed at evaluating the duration of its execution. The primary objective here is to conduct a performance test for a function named simplotl. This function's role is to simulate noisy correlations between the daily returns and future returns of stocks. The test involves various parameters, including historical daily returns, future returns, the number of stocks, the number of trials, the noise scale for future returns, as well as the minimum and maximum returns and weights for the stocks. By recording the time it takes for this test to run, developers or data scientists can assess the efficiency and scalability of the simplotl function across different configurations and datasets. This information is vital for optimizing the function's performance, ensuring it can manage larger datasets effectively and thus improving overall performance and functionality. The code snippet appears to be part of a program designed for conducting simulations and plotting exercises related to financial data. It begins by measuring the time taken for the execution using the magic command time. The primary function in use is simplotl, which is called with a range of parameters such as the test name, current daily returns, future mean annual returns, number of stocks, number of trials, noise scale for future returns, minimum and maximum returns, minimum and maximum weights, and additional arguments specified in @pargs. The objective of this code is to perform a specific test, labeled test F, focusing on noisy returns and correlations within a financial context. It seems to be part of a larger analysis or simulation that might be aimed at predicting future returns or optimizing a portfolio. By running multiple trials with different parameters, the code assesses the impact of noise in the returns and correlations on the simulation's outcomes. Such an analysis can provide valuable insights into the robustness of financial models and strategies when subjected to uncertain or noisy conditions. In summary, the code snippet is utilized for testing the effects of noisy returns and correlations on financial simulations or analyses. This helps in understanding the performance and behavior of financial models in real-world scenarios, ensuring they are robust under variable conditions. The provided code defines a class named problem, which implements a problem optimization framework tailored for fine-tuning the parameters of a portfolio system. This class offers key functionalities essential for optimization. First, during initialization, it allows users to create a problem object with specific keyword arguments designed for simulations. This feature ensures that users can customize their instances as required. A fundamental aspect of this class is its fitness calculation method. This method is responsible for determining the suitability of given parameters by simulating random portfolio trials and computing performance statistics from these results. Specifically, the class defines two primary fitness objectives. The first objective assesses the mean difference between the arithmetic mean daily return for adaptive and rebalanced portfolios, while the second objective evaluates the mean of the maximum drawdown for all trials of the adaptive portfolios. These objectives are based on simulation results and are negated since the optimization process assumes minimization objectives. The method emphasizes the necessity of using the mean rather than the median for these fitness measurements, indicating a preference for capturing an average performance trend. The class also includes a method, getBounds, which provides the search space boundaries essential for the optimization algorithm. These boundaries set the permissible range for parameters such as min returns, a max return delta, and max weight, which are subsequently utilized by the sim_minitricles function. Additionally, the method getNotch returns the number of fitness objectives used, which in this instance is 2. This information is crucial for configuring the optimization process to handle multiple objectives. In summary, the problem class encapsulates the entire problem definition necessary for optimizing portfolio system parameters. It standardizes the fitness evaluation, delineates search space constraints, and sets configurations required for the optimization procedure, thereby streamlining the solution process for portfolio tuning. The code defines a function named unpackParams that takes a list of parameters as input and unpacks this list into 3 separate variables to min returns, a max return delta, and max wage. These variables correspond to specific values within the input list. The function then performs some calculations based on the unpacked values, specifically calculating max returned by adding min returned and max return deltas. After these calculations, The function creates a dictionary named jargs, which holds named parameters that can be passed as arguments to another function called sum_minitricles. The dictionary jargs includes keys for min_returner, max_returner, min_waiter, and max_wait. With each key assigned its corresponding calculated value, this code is particularly useful for organizing and converting a list of parameters into a more structured format, a dictionary in this case, that can easily be passed as arguments to another function. Furthermore, using named parameters enhances code readability and maintainability compared to passing parameters as an unstructured list. The provided code defines a function designed to generate a plot known as the Pareto front, which illustrates the trade-off between two conflicting objectives. It achieves this through several steps. Enabling a clear visual representation of optimized solutions, the function accepts various parameters, such as the fitness values for these objectives, the experiment's name, the number of stocks, and the number of trials. Firstly, it extracts and negates the fitness values from the input array because the optimizer minimizes the objectives, whereas the goal here is to maximize them. The code then uses the matplotlib library to create a plot and add the necessary subplots. A dashed black line is plotted to demarcate the regions of loss and gain. Following this, it plots the Pareto front using connected lines and marks the data points with dots. If specific indices and names are provided, the code highlights selected data points with red dots and labels them accordingly. It also sets the title and axis labels to ensure clarity. Additionally, it formats the axis ticks to display percentages and scientific notation. Enhancing readability, a grid is displayed on the plot for better reference, and the padding is adjusted to ensure a well-organized layout. Finally, the resultant plot is saved to a file with a predefined file name. This Pareto front plot is invaluable for visualizing the trade-off between two objectives, such as maximizing return while minimizing risk. It aids in comprehending the relationship between different solutions concerning multiple objectives, ultimately supporting more informed decision-making during optimization or parameter tuning processes. This code snippet performs multi-cognitive optimization using the NSCA2 non-dominated sorting genetic algorithm TEFU algorithm. Initially, it sets up various experiment configurations such as the number of stocks, number of trials, and test name. A problem instance is then created with specific settings related to future stock returns. With certain noise settings, the optimized parameters tend to be more conservative. The NSCA2 optimizer is initialized with a generation count of 20. Subsequently, a population of candidate solutions for optimization is created, with a minimum population size of 40 to prevent premature convergence to suboptimal solutions. The population is evolved using the NSCA2 algorithm to optimize the defined problem. The process concludes by extracting the best found parameters and fitness values from the evolved population for later analysis and sorting these based on the first objective value in fitnesses. The NSCA2 algorithm is particularly adept for multi-cognitive optimization problems, enabling the discovery of a set of solutions that represent the Pareto optimal front. These solutions ensure no other solution is superior in all objectives simultaneously. Using this algorithm, we can effectively optimize multiple conflicting objectives and find optimal trade-offs between them. The code in question likely utilizes a library or framework such as scikit-optimize or another optimization tool in Python. It is designed to capture the best parameters identified on the Pareto front after performing an optimization process. In multi-cognitive optimization or decision-making, the Pareto front represents the set of optimal solutions. The variable best parameters stores an array or object that holds the best parameters found during the optimization. By applying inp round with a precision of 2 decimal points, the values are rounded for better readability and presentation. This rounding enhances the clarity of the results, making it easier to understand and potentially implement these optimal values in practical applications. In essence, this code snippet is crucial for tasks where the goal is to determine the best set of parameters that optimize one or multiple objectives. The rounded parameters provide clear insights, aiding in decision-making and the improvement of model performance or system efficiency. This code segment is designed to streamline the optimization of model parameters, focusing on minimizing the max drawdown of adaptive portfolios. Initially, it identifies the index of the best parameters based on the second fitness measure. Retrieving and unpacking these optimal parameters from the best fitness array, it then updates the test name by appending a 1 to reflect the new set of parameters. The best arguments obtained from the optimization are displayed for clarity. Using these parameters, the code simulates random portfolios by invoking the SimMiniTrickles function with the necessary arguments. The resulting simulated data is utilized to generate performance statistics, which are stored in diffstats, while the portfolio values for each trial are kept in diffportfol. To offer a comprehensive view of the model's behavior, the plotUmPer_StatSol function is employed to visualize a comparison of performance metrics such as returns and the Sharpe ratio. Overall, this automated process is crucial for optimizing model performance by evaluating various fitness measures and selecting parameters that minimize the max drawdown. This approach not only enhances the model's efficacy but also provides insights into its performance across different parameter settings. Moreover, visualizing the performance statistics aids in making informed decisions regarding the selection of optimal parameters. This code snippet demonstrates the process of selecting the optimal set of parameters for simulating random portfolios. Initially, it identifies the index of the row in the best fitness array that contains the parameter set closest to achieving the minimum absolute difference in mean daily returns between the adaptive and rebalanced portfolios. Once the appropriate parameters are identified, they are assigned to the variable bestArgSto. Using these optimal parameters, the code then simulates multiple trials of random portfolios through the function SimMiniTrickles with the unpacked bestArgSto. Following the simulation, the performance statistics of the resulting portfolios are captured in diffstats. To offer a comprehensive analysis, the code employs the plotUmPer_StatSol function to plot a comparison of various performance metrics, such as mean return and maximum drawdown, for both the adaptive and rebalanced portfolios. In essence, this code aids in identifying the best parameters for portfolio simulation and facilitates the visualization of performance differences between the adaptive and rebalanced portfolios based on those parameters. This process ultimately supports informed decision-making regarding portfolio construction and optimization strategies. This code snippet forms a crucial part of a larger program by performing several key functions to optimize and evaluate different parameter sets for a simulation or algorithm. Initially, it employs the Karpman function to locate the index of the smallest value in the first column of the best fitness array. Using this index, it then retrieves the corresponding parameters. The test name is updated by appending 3 to the original name. Following this, the code simulates numerous trials of random portfolios utilizing the identified best parameters and the existing simulation arguments. Subsequently, it plots a comparison of various performance statistics derived from the simulated data. These steps collectively facilitate the selection of the best performing parameters based on a specified fitness function, which is instrumental in optimizing the algorithm or simulation. By comparing different parameter sets, developers can effectively fine-tune their algorithms or simulations to achieve enhanced results and performance. This code creates two lists, listStatus and list names. The listStatus contains the indices of elements that need to be highlighted in a Pareto plot, while list names holds the corresponding names of those elements. Highlighting specific elements in a Pareto plot can be crucial for drawing attention to the significant contributors to the overall outcome. By specifying these indices and names within the code, the Pareto plot can be tailored to emphasize the most important data points. This customization aids in identifying key contributors or outliers in the dataset, facilitating more informed decision-making based on the highlighted information. The code snippet appears to be used for generating a plot that displays the Pareto front along with the best fitness values. The function plot Pareto front is called with specific parameters, which include the best fitness values obtained from the Pareto front, the name or identifier of the test being conducted, the number of stocks being analyzed, the number of trials conducted, an index list for identifying points on the Pareto front, and a list of names for those points. The primary purpose of this plot Pareto front function is to take these parameters and generate a plot that visualizes the Pareto front, highlighting the best fitness values discovered during the optimization process. This visualization aids in illustrating the trade-offs between different objectives or parameters being optimized simultaneously, showing the best possible outcomes that cannot be enhanced in one objective without compromising another. Visualizing the Pareto front is essential in multi-objective optimization scenarios where there are conflicting objectives. It helps in understanding the trade-offs between different objectives and in selecting the most appropriate solution based on the best fitness values. Therefore, by calling this function with the specified parameters, a plot will be generated to represent the Pareto front, providing an effective means to visualize and interpret the results of the optimization process.